And hello, welcome back, OpenFOAMers. No, not OpenFOAMers. YouTubers. I'm not doing an OpenFOAM series, but yeah, this channel is a lot of OpenFOAM videos. But anyway, the principles talked about in this series, they are turbulence modeling. We're going to continue that discussion, and these principles do not just apply to OpenFOAM, but many types of CFD software. So today we're going to talk about continue talking about the kOmegaSST model. Shear stress transport, and we're going to talk specifically about this blending function. So this is the blending function over here. It looks like a big mess. So I'll just write that down first. The blending function, blending function F1. Alright, so this is from the kOmegaSST model on cfdonline.com. F1 equals the hyperbolic tangent, and then a curly brace outside. I'm just going to copy exactly another curly brace, and this one is to the power of 4. To the power of 4. Okay, there's a minimum, and then there's a minimum inside, min, and then I'll put a square bracket, and then it says max, and normal bracket, and then I'll have a square root k divide by beta star omega y, which is 0.09 times omega, which is over here. Okay, so beta star omega, this one is actually just this beta star omega star. Remember this one? They use a different notation, so I'm going to use omega. Alright, beta star omega, so it's a omega y. Okay, remember over here the omega is different. Over here the omega is different, so I used omega star for that. Omega y. Hopefully you know why, because this omega here is actually beta star omega here. Yeah, so it just depends how you define omega. In CFD codes, they probably define it differently from the literature or from the base definition of omega, like this. Okay, reason being, my guess is this is because it's more computationally efficient to have omega defined like this over here, rather than omega equals epsilon over k. I'm suspecting that. If I ever get to the point where I can explain it, then I will, but not now. Okay, so next one is 500 mu. Okay, 500 times the kinematic viscosity divided by omega y square. So there's omega star y square. So omega star is omega over beta star, or omega over c mu. So I'll just write omega, and then I'll put c mu on top. Okay, where c mu is c mu equal to beta star. Okay, the next one is max of this, and then the minimum will be, okay, so there'll be a 4 sigma omega 2, 4 sigma omega 2. So this is a constant k divided by cd k omega. You'll go through each of these very shortly. Y squared. Okay, so this F1 looks like a horrible mess. It's a blending function, but the hyperbolic tangent is as such. We can just go to Excel and I'll just do blending function here. Okay, So x and then tangent x, hyperbolic tangent x. So we'll just plot a graph 0.01 and first hyperbolic tangent of this. Okay, and then we'll just quickly draw a chart in Excel. Okay, so let's draw a chart. Insert scatter plot. Okay, so this is a graph of y equals to a hyperbolic tangent of x. You can see the curve is pretty smooth and it varies from 0 to 1, which is exactly what we want our f1 to do. We want f1 to vary from 0 to 1, and you can see it's a very smooth curve. Okay, I think Fluid Mechanics 101, yeah, Dr. Aiden, I think, he talks about this in his video. So I took inspiration from that, but I'm going to go a little bit further into discussing all of this inside here. Okay, so we start from inside. We ignore the square first. So let's evaluate these functions, right? There's a minimum and then a maximum. All right, so let's go from the inside and work our way out to see what these are. So I'll get rid of all of this. And okay, first okay, OpenFOAM, YouTube, Paint 3. Okay, so it's just my various blackboards. Okay, so let's deal with this maximum function first. So as with all maximum function, let's say we have curve 1 and curve 2. So curve 1 does this, and then function 2 does this. All right. If we want the maximum, so this is I'll use a pink curve then. If we want to use the maximum, then we are not going to use either of the curve. We're going to use this section of the curve. All right, this section of the curve and this section of the curve. So if this is y1, y2, the y max equals to maximum of y1, y2, and that's all we are doing. That's what the maximum function is. And then okay, so I want to take this hybrid curve I highlight in purple. All right, so that's what this thing is doing. I haven't discussed the actual shape of this yet. We'll come to that in a moment. And then we want to have a minimum of this because we have a curve like this here. You see this extra little function. Don't know what that is, but let's just draw an arbitrary curve. Just draw this, and then we want the minimum. All right, we want the minimum. So y3 min equals to minimum. Okay, a maximum a1, y2, and then u2, y3. So okay, so that's what this complicated function is about. So this is y3. I shall use this color. y3 is here. So if you want a y3 min, I will use a green curve. So y3 min, so it's going to compare between this purple line, all right, this purple line here, and this blue line. So just ignore what the y1 and y2 is because we kind of took the maximum of that already here. So that's the purple curve, right? We took the maximum of that, and now we want the minimum. So I'm going to use a green curve. So minimum is between the blue line and the purple line. So I will highlight this part, then I want the minimum over here. Okay, so that's what the minimum and maximum is. Then comparing between these two, let's say the purple curve goes like that, then I will take this part of the graph. So this minimum of the maximum will look something like that. All right, so this is what this complicated function here is doing, the minimum of the maximum. And then of course what the curve does is to take all of this and then you just put it in a hyperbolic tangent graph, right? Okay, where it will, regardless of what it is, it will be between 0 and 1, and it will vary smoothly, okay, depending on how this function looks like. Okay, so depending on how this function looks like, it will vary smoothly as such. So this is what the minimum and maximum does. So we want to see what y1, y2, and y3 are. Okay, so we can like plot this on a graph. So what do this, let's say y1, okay, I won't use y, I'll just use the function string. What does this k square root k omega y, this and this thing look like? Okay, so there are two regions, of course, you want to discuss at least, but okay, most importantly, we want to discuss near the wall. Why? So we want to discuss near the wall. Why? Because we want k omega to activate near the wall. And for k omega to activate near the wall, f1 should tend towards 1. So f1, why does f1 tend towards 1? When f1 tends towards 1, this extra term that is derived from the k epsilon model will disappear. So f1 should tend towards 1. So f1 is the degree to which the k omega model kind of activates. Okay, so f1, okay, f1 is the degree, okay, to which k omega model activates. Okay, so we want f1 to go near 1 at the wall. So one of the important things is to, of course, derive this wall function. Okay, and then we see how does f1 change in, let's say, the viscous sublayer VSL, and then the log law region where you have a turbulent sublayer. And then of course you want to see how that and then see how this velocity profile goes for large y plus values. And of course this is for flat plate boundary layer flow, which we can assume applies to most flow types except convection and flow with strong pressure gradient. Okay, so why is this important? Because this will negates the constant shear stress hypothesis. Okay, so remember when we derive our wall function equation, we had to assume that the shear stress is constant in order to derive our wall functions, at least for smooth wall and sometimes even for rough wall as well. Okay, let's see, where did I put my wall functions here? Check this out. Yeah, so this is just a flashback to that. I put it into the kOmegaSST. Okay, I'll put this here. Okay, so this is just a recall for you. Wall function is not wall function, tau apparent. The apparent shear stress is constant with respect to y. This is only true if the pressure gradient across x is very small or negligible. So this is a boundary layer flow assumption. Okay, but for simplicity's sake, we will just assume this, and we will carry out what do you call that? Yeah, we'll carry out the integration, or rather the analysis for a smooth wall first. Okay, so that's that. Okay, so how do these actually vary with y? Because you want to eventually see how f1 varies with y, or at least y plus, right? Okay, so that's very important. So it just gives you a visualization how this blending function works. So for that, we need wall function for k and omega. Alright, we need wall function for k and omega. So alright, so we need wall functions for k and omega. Okay, so omega should vary with y plus, and k also. Alright, okay, so anyway, this CD thing, I don't want to overload you too much data, but I have to say this CD thing is this function here. I'll get to that a little bit later. Okay, but anyway, we shall continue. Alright, we shall continue. Alright, so we will deal with this first two terms first. Alright, so where do we find these wall functions for k and omega? So if you look at the CFD online, we go for near wall treatment. Okay, this is a LES simulation. I'm not going to go into that yet. This is the near wall treatment for k omega models. So we can look here, and then this page will pop up. Okay, is this page I have open here? All right, so I mean, the standard wall function is to have a zero gradient near the boundary, but that's not very helpful for us. We need something more concrete than that. So we have this automatic wall treatments here. Okay, and then you'll see how omega actually changes with y in the viscous sublayer. So viscous sublayer and log law region as well. Then you also have this friction velocity, okay, which will help you in finding this Kp. It's not going to go through in too much detail on the derivation, but you can look at here, because they'll have this page called two equation here, wall treatments here. You open that up and you'll get this page. You can look in the standard wall functions. They go into a little bit more detail how you get all these things, and if you take a look at the literature, and this is how omega and k actually change with y plus. All right, so how do these actually come about? I'll just show you briefly. This is okay, just ignore this page. Okay, if you look at I think this is one of the documents by Fangqing Liu Fangqing. It tells you, this is a project of description of how wall functions are implemented in OpenFOAM. You scroll to I think chapter 1.3.2. It will show you that in the k omega model you'll have these two equations. I think there's a typo in this one, but yeah. And then okay, where did this come from? Okay, it cites this paper, I think one of these papers. All right, so it has a citation here, citation number 4, which you can scroll down and look for citation number 4. It's near wall behavior of Reynolds average Navier-Stokes Rentz turbulence model and implication for wall functions. So this is the paper you can look for. Thankfully, I think now it's available. Okay, so should be available, and this is the paper they're talking about. So okay, anyway, the printer is activating for some reason, but never mind. Yeah, just bear with me for a while. I'm gonna end the video soon, and yeah, next video I want to talk more about these wall functions, how we derive all these wall functions for k and omega. So I'll see you in a bit when this printer like deactivates. Anyways, 20 minutes anyway. So thanks for watching. Leave a like and subscribe if you do find it useful, handy, and see you guys next time. Bye bye.